Jai Hind everyone, welcome to the lecture series on Discrete Structure and Theory of Logic, and I Megha Gupta, Assistant Professor in CSE Department at AKGEC Ghaziabad. Today's topic is Abelian group. It is the topic of Unit 2, which is according to the syllabus of AKTU exams. So let us start with the Abelian group. So the table of contents which we cover today are abelian structure, what is algebraic structure, what is binary operation on a set, and what are the properties of an algebraic structure, what is semigroup, monoid, and then group. Then we come to the abelian group, and after that we follow with the properties of the abelian group, and we will discuss about some questions. Now first is, what is algebraic structure basically? So we can say that a algebraic structure basically in a set can be represented as a non-empty set. We consider a non-empty set, that is G, equipped with one or more binary operations, is said to be an algebraic structure when G is operated on any operator which we represented by a sign, that is asterisk. So in this slide, as we represent it as G with the sign asterisk is an algebraic structure. Here we suppose that. So star is an operator which is vary according to your need. Means if I consider that natural numbers with star, or we can say that 1 with plus sign, so plus sign here represent the operator which we generally represented by the asterisk sign. And also the 1 is the element of a set and minus is the operator which we basically represented by the sign star. So G here is a set which consists of elements, or star is an operator which is vary according to your need, and this structure is known as algebraic structure. Here one more structure is algebraic structure, that is R, which will equipped on two operators, that is plus and dot. So R is also an algebraic structure with two operators, that is plus and star. So this is the definition of algebraic structure. Now come to the second topic, that is binary operations on set. So basically, as we all know that set, what is set? A set is the collection of distinct elements. So here there are so many sets given here, like n. N is the set of natural numbers, and Z is the set of integers, and Q is the set of rational numbers, and R is the set of real numbers. So what is binary operation? Suppose G is a non-empty set. Non-empty set means G minimum consists of one element. So this is known as non-empty set. Then if we calculate G cross G means Cartesian product of G with itself. Then we can write it as order pair of A comma B, where A belongs to G and B is also belongs to G, because we find G cross G. If function G cross G implies G, then F is called binary operation on set G. Means the order pair AB under the function F is denoted by AFB. Image of the order pair under the function F is denoted by AFB. So this is the binary operations on sets. Binary operation on G is sometimes said to be binary composition, because if we consider that star is a binary composition in G, then we can write it as A star B, where A and B both belongs to capital G. G is a given set. Therefore, small g is closed with respect to composition denoted by star. Now, let us take an example that an addition is a binary operation on the set of natural numbers. So the sum of two natural numbers is also a natural number. So the closure property means the binary operation representing on the elements of the set of the given set is then the resultant with the operation will also belongs to that set. That is the closure property in mathematics, we can say. So if any given set is follows the operator follows the closure property, then we can say that the group follows the algebraic structure property, or we can say that they follow binary operations on set. So here the same example with the natural numbers we take. The sum of two natural numbers is also a natural number, and let us explore this by taking an example that the two natural number like 4 plus 7, 4 and 7 belongs to natural number, right here. So 4 and 7 is 11. The sum of both also belongs to natural number. This type of things is come under closure. Property, and this is known as binary operations on given set. But if I take operator like subtraction, in the next example I take operator as in subtraction, and the set is same as natural number, then n means natural number set is not closure with respect to the subtraction. So it is necessary that according to the operator, the G is closure or not. Then according to that situation, we can say that it follows the binary operation, or we can say that it follows the algebraic structure property. So if we want to prove that any set with its operator follows the algebraic structure, then we must prove it as closure property. Now, properties of an algebraic structure. There are some properties of algebraic structure we studied. That what is commutative? Commutative is basically here, if I take the same definition, that let star be a binary operation, as we earlier said that always we take asterisk as an operator. So here we take asterisk as in binary operation on any set A, then we set to be commutative star in A if A star B is equals to B star A. Or if I take here an example that set of natural number, then we take two numbers 2 and 3, then 2 plus 3 set of natural number with addition operator, right? Then 2 plus 3 is 5 and 3 plus 2 is also 5. So this property is known as commutative property. After that, the second property is associativity. Here also we consider the operation is star and the set is A. Then the associative consists of A star B star C is equal to A star B star C. Here if you see that here the only difference is the difference of the brackets, means here first we solve it A star B and here first we solve B star C. If they both are equal, then we can say that the operator, the given operator follows the property of associativity, right? Now come to third property, that is identity. Identity for any algebraic system. We consider an element E. For identity, we consider an element E which belongs to A. Is said to be the identity element of A if A operator with E gives A, or E operate with the A always gives A, where A belongs to the given set and E also belongs to that set. So E will be the identity element. So for this we take an example here. That A star E equal to A. We consider the set of natural numbers with the multiplication operator, right? If I take 2 and we will and I will get the resultant 2. So what should we multiply in it? So we get 2, the 1, right? If I multiply 2 by 1, then we will get 2 as in result, right? So here The 1 is the identity element. So this shows identity property of an algebraic structure, right? And it should be unique, right? For the fourth case, that is inverse. Inverse means if I consider A, set A with operator star, then and the identity element is E, then the inverse says that A star B is equals to E, where here B representing inverse of A, right? Or we can write it as A star A inverse equal to E. For the common example, we take a verb. If I take here 2, what will be the inverse of 2 so that we will get 1 as an identity element? So if I take 1 by 2 here, then will we get 1 as a result, but 1 by 2 is not a natural number. So in case of natural number with the multiplication sign, there is no existence of inverse possible, right? So this is the inverse property. Now come to the next thing, that is semi-group. So first thing is algebraic structure and second thing is semi-group. So what is semi-group? Continues with the set A with the operator star is said to be semi-group if it follows two things. First one is star is closed operation on A, means the given operator star is closure on the set, on the given set. First thing is that, and second is star follows an associated operation. Star follows an associative operation means associativity which basically defined as A star B star C equal to A star B star C, as I already explained it, right? This is the associative operation. If any set with the given operator follows these two properties, then this algebraic structure is known as semi-group. Here we take an example of natural number with the plus sign. So let us check it is closure or not. Natural number with plus sign. If I take 2 plus 3, it will give 5. So 2 belongs to natural number, 3 belongs to natural number, 5 is also belongs to natural number. So therefore this is closure under operator plus, right? Now second thing is associativity, and as we previously take that plus is associative under natural number, means it follows this thing. So natural number with the sign of plus is a semi-group. Here are some more examples like natural numbers with dot operator. Natural numbers is minus operator is not a semi-group, because as I said that 2 minus 3 is minus 1, which is not a natural number. That's why it's not a semi-group, because it is not closure under subtraction, right? So this is the definition of semi-group. Now come to the monoid. Monoid basically a group which shows property of an identity element with respect to operation, with respect to given operation star. So in other words, we can say that an algebraic system M with operator star is called a monoid if it follows three property. First thing is it is closure under that operator, second is it is associative under that operator, and third one is if the identity element is present of the operator under the operator of the set, then we can say that it will become a monoid, right? So in case of monoid, we have to check three things. One is closure, and second is associative, and third one is identity, right? So if I take the natural number with the plus sign, as we previously proved it, that is closure, that is associative. Now check the identity element. If I take 2 as an example, then identity element will be A star E will give A, right? So what we should add in 2, so we get 2 as a result. So we should add 0, but 0 is not a natural number. 0 is not a natural number. So natural number with the plus sign is not a monoid, because the inverse of elements of the set under star operator is not present. So this is the monoid. So monoid consists of 3 properties, as you say: closure, associative, and then identity. So I take another example, natural numbers with respect to multiplication. So this is a set of natural numbers. Here I have to check 3 properties: closure, associative, and identity. So we know that product of 2 natural numbers is again a natural number. It is a very simple thing, like 2 into 3 will give 6, and they all 3 are natural numbers. So multiplication is closure in nature with respect to natural numbers, right? Now come to the associative. Yeah, multiplication is also associative under natural number set. Under natural number set, then third property is identity. In case of A, star equal to A, this is the definition of identity. If I take any element like 2, then operator is multiplication. So what should we multiply with 2 so that we get 2? So only 1. So in case of multiplication, the identity element is 1, and here we use the set of natural numbers, so this will become a monoid. So given algebraic structure, natural number with the operator multiplication is a monoid. Now come to the sub-semi group and sub-monoid. Sub-semi group, basically let S be a semi group and let T be a subset of S. If T is closed under operation star, then T star is called a sub-semi group of S star. Means if any set with a given operator is a subset of any other set with given operator, and they both follows the closure property, then we can say that the subset set is sub-semi group of that set. Here we take an example of natural number with dot operator is a semi group, and T is the set of multiples of positive integers M, then T dot set of T with dot operator is a sub-semi group, right? Now come to the sub-monoid. Sub-monoid is also same as sub-semi group, like let S star be a monoid with identity element E, right? Because in case of monoid we take the identity element, and let T be a non-empty subset of S. Then if T is closed under the operation star, then E belongs to T, then T star is called a sub-monoid of S. So this is sub-semi group and sub-monoid. Now come to the group. This is very important. Come to the group. So in case of group, any algebraic system with set like G and operate on operator star, if it follows 4 properties, then we can say that the algebraic system becomes the group. What are the 4 properties? The 3 properties are same as in monoid, like closure property, associative, and existence of identity element. And one more property here is added, that is inverse. That is existence of inverse, right? So first property is closure property, as we discussed already. Second is associative, and third one is identity, and last one is existence of inverse. So in case of existence of inverse, we say that A star A inverse will give identity. This will be the proper definition of the existence of inverse. So if any algebraic system follows these 4 rules, then we can say that it will form a group. So for this we take an example of real number with the operator plus, with the operator addition. So let's check real number with plus operator is closure or not. Yes, it is closure, right? Yes, it is associative because plus operator is always associative, and in case of plus operator we have identity element, that is 0, and 0 will be in real number. So it is present in case of plus operator with real number. Now come to the inverse, right? Inverse means what will be the inverse of 2 so that we get 0? So that we get 0. So what should be multiplied with 2 so that we get 0? So we get 0 as an element. So if, sorry, here the operator is plus, so need not to be multiplied. So if I take minus 2 as an inverse of this, then we will get 0, and minus 2 is come in real numbers. So real numbers with the operator sign plus is will become a group, right? So let us take now come to the abelian group or commutative group. We can say that abelian group basically a group which abelian group is basically a group. It means it follows all previous 4 properties, and one more property is added in a case of abelian group, that is commutative. That is commutativity. That's why we say that abelian group other name is commutative group. A group G is said to be abelian or commutative if in addition to the above 4 postulates the following postulate is also satisfied. The 4 postulates will be closure, one is closure, second is associative, and third one is identity, fourth one is inverse, and last one is commutative. So if all the 5 properties are proved for any group, for any set with respect to its operator, then we can say that the following algebraic system will become a abelian group. So this is a abelian group, right? So algebraic system basically consists of 5 things. First one is your algebraic system, second is semi-groups, then monoid, then group, then abelian group. As I see in this, you see in this diagram that algebraic structures consist of all 4. Means if I want to check that the group is abelian, then always I want to check the closure property, right? Or if any group, any set on the given operator is closure, then only we set this follows algebraic system, right? In case of semi group, one more property is added, that is associative, right? In case of monoid inverse, we check inverse. In case of group, we check identity. Sorry, in case of monoid, we take identity, and in case of group, we take inverse, right? We take here, we take inverse in case of group and identity in case of monoid. And last one is commutative, right? So if I check abelian, then I have to check all 5. If I want to check for group, then I will check for all 4. Sorry. If I will be go for monoid, then I will check 3 properties. If I go for the semi groups, then I will check for 2 properties. If I go for only algebraic system, then I check only 1 property, that is closure. So this is the basically the algebraic systems or the abelian group concepts. Now come to the properties Properties means a group with respect to G holds identity element which is unique in nature, inverse element which is unique in nature, and third one is cancellation law. Cancellation law means if I have A star B equal to A star C, then we can say that AB equal to C. That is left cancellation, means the element of left will be cancelled out, and here the element of right will be cancelled out, so this is known as right cancellation law. And the fourth one is if I have A star B and whole inverse is equal to B inverse star A inverse, these all four properties, if any group holds, this is also a property. And second, in a group the identity elements is its own inverse, right? For example, 1 is the identity element in case of multiplication, so its inverse will be, so we get here is as 1, the inverse is itself, so this is the point. And next is order of group. Order of group, basically the number of elements in the group is called order of that group, right? If I take any group like 1 2 3 4 with star, so that means the order. The finite group means if the order of the group is finite like this, so this is a finite group. Now take an example that show that the set of all integers is a group with respect to addition. Set of integers, we can say that Z with respect to addition, we have to prove that it form a group. So in case of group, we have to check the 4 properties. One is closure, second is associative, third one is identity, and fourth one is inverse. So let us check for closure property. So in case of closure property, A plus B belongs to Z. Example, 2 plus 3 is equal to 5, right? So 5 belongs to Z. So here it follows the closure property. Second is for identity, as we all know that summation plus always follow associativity. Third one is identity. In case of addition, we have identity element which is equal to 0, right? So and 0 it belongs to Z. So the identity element is also present because the definition of identity is A star is E equal to A, right? Now in case of inverse, we say that A star A inverse equal to E, and E is the 0 element. So what will be the inverse? 0, right? Means A plus minus of A will gives 0, and minus of A means negative integer. Negative integer is also here we take, so we can say that integers with respect to positive sign is form a group. Let us check for abelian also. And plus operator is always commutative in nature, as we all know that. Then Z with respect to plus sign is form a abelian group. Now take another example. So here we take a set of non-zero real numbers is a group with respect to multiplication. Set of non-zero real numbers we take with multiplication. Non-zero real numbers, if I take, then we will represent it that with star sign, right? So it follows closure because real number set. Multiplication is always associative in nature. Then identity, 1 is the identity in case of multiplication, which is real in nature, so it is also true. Now come to the inverse. Inverse means A star will be give identity, that is 1. So here I use 1 by A, and 1 by A is real in nature and it is a non-zero element. So we can say that here R is having inverse, right? Now check for commutative. Yes, star is commutative, or multiply is always commutative in nature, so it is a abelian group, right? Now take another example, that is R is not a group with respect to multiplication. R means simple real number set with respect to multiplication, right? Yes, 0 belongs to R, right? and multiplicative inverse of 0. What will be the multiplicative inverse of 0? What we take here, it is, which will give 1. Yes, it is closure in nature. Yes, it is associative. Yes, the inverse, the identity element is also present in case of multiplication, that is 1. But in case of inverse, it will fail out. It will fail out like if we take an inverse of 0. So how will we get 1 as an output? No, this is not possible in any case. So R is not a group in case of real numbers with multiplication. Now come to the example number 3, that is show that all the set of strings is a monoid under the operation of concatenation of strings. Basically concatenation means combining of two strings, like one string is Megha, right? And second string is like Gupta. So concatenation means it will print Megha Gupta. This is concatenation. So I have to prove it will form a monoid. In case of monoid, we have to follow 3 properties, that is closure, associative, and then identity, right? So it is closure or not? Yeah, if I take this and this, right? S1 concatenate with S2, right? S1 is a string which belongs to the set of strings. S2 is a string which also belongs to a set of strings. Then concatenation of both these two is also belongs to that. That means it is also closure in nature, and you all know that plus sign in case of so in case of concatenation we are also doing some addition of two numbers, right? So concatenation of string is always associative. Now check for identity. If we have null string, then if I add this this null string in the given string, then we get the same string as an output, right? So for this, let us take example that S1 is Megha, right? And lambda represent null. Null means nothing, right? So if I take S1 plus lambda, which I get Megha only, right? Which is S1. So in case of string set, we have lambda, that is null string, as an identity element. So S is a monoid, right? Because identity element is always a subset of every set. Sorry, null set is always a subset of every set. So that in this case identity is also present, and we can say that S is a monoid, but S is not a group because inverse for any non-empty string doesn't exist, right? Now take another example 4. Let Z with star is an algebraic structure where Z is the set of integers and the operation defined this. Operation here is defined maximum of n and m, maximum of n and m, right? So it is closure in nature, as I take 2 and 3, they both are integers, and the maximum of these two is 3. Maximum of 2 comma 3 is 3, which is also an integer. So it is closure in nature. And next is maximum of ABC. If I take here, for example, B is the maximum, right? And BC may fir B maximum. B is the greatest number. In case of this, B is maximum and A star B is maximum. Then it is associative in nature. Now check for identity element. There is no integer x such that A star x equal to max of AX equal to A. So it is not a monoid. Means in case of this given set, we doesn't have any element which will be formed as identity element. So in case of this example, it will not become a monoid. It just become a semigroup. Now come to the next example, that is let S be a finite set and Fs be the collection of functions under the operation of composition of function. Composition of function means FOG, GOF, which will operate on more than one functions, right? So justify it ki it will become a group or not, right? So it is closure. Yes, it is closure in nature because the resultant function will be a part of that function, right? Associative, yes, always composition is associative in nature. Now come to the identity one, right? If I take identity function which is mapped over S to S, then if I take F1 O identity, then it will always give F1. So F1 is monoid, Fs is monoid but not a group, because inverse of a non-bijective function doesn't exist. Now come to the example number 6. Example number 6, we have to prove this, right? So for this, prove this, I have to take consider that A star B inverse A inverse, right? Then if I multiplied it, right, AB B inverse AB A inverse, or we can write it as by associative property, that is A B star B star A inverse, right? This is one element, this is second element, and this is according to inverse property, this will become identity, right? So it will become E. Now A star E is A, so A into A inverse is E. So we will get identity element in case of this expression. Similarly, we can show that this into this is also identity. So if they both are giving the identity element, hence this is equal to this. If G comma star is a group and A belongs to that group element of G basically, such that A star A equal to A, then show that A equal to E. Where is the identity element? It is given that A star A equal to A. Then A star A will be written as A star E here, because A star E is equal to A according to identity property, right? So according to identity we can write it at this. So from this, by cancellation law, by the left cancellation law, we will get A equal to E. So the result follows here. Thank you so much, and we will discuss more topics in further lectures.